So let's start off by talking about the heroes of the Tidyverse. So these are the titans, right? They're pervasive, they're everywhere, they're doing all the heavy lifting, and you're probably using them multiple times every single day. Now, what would a hero be without a villain? To the best of my knowledge, there are no villains in the Tidyverse. Maybe I just haven't plumbed the dark side deep enough. And then we come to the sidekicks. The sidekicks are always there, kind of lurking in the shadows, just outside the hero's immediate limelight. They're not as flashy or as glamorous as the heroes, but they're there getting the job done and often helping the hero to look his best or her best and do their jobs. So let's start off with our first dashing duo. We have Map and imap, represented by the hero, Han Solo, and his trusty sidekick, Chewbacca, Chewie, or as Leia likes to refer to him, the walking carpet, which I think is grossly unfair. Map and imap have essentially the same function signature. So they accept data as the first argument, and then a function as the second argument. Where they differ is that map is looking for a function of one variable, whereas imap is looking for a very specific function of two variables. Why do I say specific? Well, it's different to map2. Map2 is looking for two data variables. imap is looking for something slightly different to that. We'll get back to that in a moment. So supposing, for illustrative purposes, that we have a vector, and I'm not sure whether this is even visible on the screen. It's a named vector, right? A series of values, of heights, and it's named, which means that each of those values has a name associated with it. You can name a vector in R. Now, if I was to use the map function to iterate over that height vector, providing a very simple function, it's the identity function, basically, I would get back a list, and that list would contain the values, and the index for that list, or the names, would be the names extracted from the original vector. So far, so good, quite simple. What about imap? Well, now with imap, we need to have a function of two variables, and those variables serve a very specific purpose. The first one is for the data, but the second one is for the index. So from within this function, we can reach up and pull the index into the function as well. And this has some very useful consequences. So in this case, I've got a very trivial function. What it does is it takes the index and the data, concatenates them together, and just returns the results as a string. So I've now got a list of strings. But you can do something very cool with this. And it's something that I end up doing actually rather frequently, disturbingly frequently. It's quite complicated when you've got two remote controls, and you have to remember which one is the remote control and which one's the pointer. OK, so let's look at a slightly different set of data. So now I've got a list, and the elements in that list are very, very simple. It's a series of single record data frames, and they're labeled elements. And here I have the names of the characters, and then they're as the index, and then their physical characteristics in the data. Now, if I was going to work with this data, I would want to firstly concatenate all those individual data frames together. And I would want to have those names in the data frame as well. imap will do this for you. Right? So here, I have a function. That function, again, data, then index. And within the function, it's doing something very simple, taking the data and then using mutate to insert a new column. And that new column has been populated with the value from the index. The result from imap is a list. Well, there's actually a variant of imap called imap_dfr. And the result there will be a concatenated data frame. That's apparently been deprecated. So I'm taking the results, using bind rows to squish them all together. And this is what we end up with. Right? data where the index has actually now been incorporated into the data frame. If you look at this carefully, you may object to the fact that name is at the end. I would definitely want to have name at the beginning, and indeed I could have set that up within the function. But this is actually a convenient segue into the next dynamic duo, Frodo and his sidekick Samwise, representing select and relocate. I'm perfectly confident that most of you will have encountered select, right? It allows you to take a data frame and pull out an arbitrary subset of the columns in that data frame in whatever order you want. Right, so here's my original data frame, and I've shuffled things around, just specifying the order of the names of the columns in which I want them, leaving one of them out, dropping the gender column. I can also use select to move columns around. So for example, frequently I find I'm going to move a column to the beginning, right? Easy enough. Simply specify the name of that column and then use the everything helper function from tidyselect to basically inject all of the remaining columns in the original order after that first column. You can also move a column to the end. This requires a little bit more fancy footwork, right? Firstly, you need to extract that column. So in this case, I'm moving ID to the end. I need to extract that column first. So I'm pulling it out. Then I insert all the remaining columns and then pop ID back at the end. It's an easy enough recipe to remember, but it's kind of clunky. Okay, what about inserting columns at positions that are not the beginning and the end? Well, this can be a little bit more challenging, potentially laborious. Basically, you have two options at least. The one is to specify all of the column names in precisely the order that you want them. This is fine for a narrow data frame like this one. But if it's a very wide data frame, then listing all those columns, well, it's going to be a real pain. There are some tools that will allow you to do this a little bit more concisely. So, for example, you can use the range operator. It's kind of moot here because I've only got 2 columns on the left. And you can also use everything to just plonk in whatever remains. It's fine. But surely there must be a better way, right? And there is, courtesy of our sidekick, relocate. Now, relocate has 2 arguments, or 2 extra arguments, dot after and dot before. And these allow you to specify the column relative to which you want to insert that column. So here, for example, if I want to move name to the second position, I can specify that I want it after ID. Equally, I could specify that I want it before height. Same. You can also use the same operation to move a column over to the right, to the end, right? We saw that before, potentially this could be a fairly tricky thing, or laborious thing, but here we can simply use the after option and last call, which also comes from tidyselect. This is very handy because, columns have a nasty habit of moving around or being replaced. By using last call, you don't have to explicitly specify what you expect the last column to be. Last call will give it to you anyway. Okay, just to mention that it's not just a single column that you can pass to relocate. You can pass a series of columns or indeed a range of columns. That works perfectly fine as well. How many of you recognize these chaps? Many of you, I suspect, are my generation then. Okay, so here we have Wayne and Garth. And they are representing case when and case match. Okay, so suppose we have some data that looks like this. Now here in the gender column, and I know one should really not use gender for an example, but I have a lack of imagination, I suppose. So here in my gender column, I've got this, some values that are clearly missing, but they're being represented by the string n/a, and this kind of thing occurs more frequently than I'd like to admit. So in order to clean this up and make it more useful from a computational perspective, I'd like to replace these NA strings with the actual NA value. Now, there are a couple of ways you could go about doing this. One is to use like the inline conditional operator, if else. Right? And this is basically within a mutate. I'm saying, well, if gender is equal to NA, then replace it with the NA symbol. Otherwise, just replace it with what it will. Just use what it was originally. This works fine until things in your data become even messier. So supposing, for example, it's data from a form, maybe, and some people have encoded their gender using a single letter, and others have used the full word, sometimes uppercase, sometimes it's lowercase. So things can get a bit messy. And of course, you can use exactly the same approach to deal with this as well. Just tack on another if-else, right? And you just keep on adding if-else clauses until you've dealt with all the warts in your data set. This is going to become, well, a little bit clumsy, and it's going to become more difficult to maintain. So, case when. Our hero in this case allows us to deal with this in a very neat way. Case when accepts a series of formulas, and each of these formulas consists of a logical predicate on the left-hand side. So, for example, gender equals NA string, and the associated substituted value on the right-hand side. And the way that case when works moves through each of those formulas one at a time, and whenever that logical predicate on the left evaluates to true, it uses the value on the right. If none of them are true, then it'll use the default value specified at the end. This is a very general purpose tool in the sense that the stuff that goes into that logical predicate can be anything within your data. So you can reference other columns in your data, you can reference global variables. It's overkill for this particular application. So we have case match. Now case match accepts the column that you're interested in as the first argument. And this means that each of the subsequent formulas is now much more focused. You've got the value that you're matching on the left-hand side and whatever you're wanting to replace it with on the right-hand side. And there's a bit of flexibility here. You can specify a vector of values, so both uppercase and lowercase m are going to be replaced with male and full. But unfortunately, the only downside to this approach is that it doesn't cater for regular expressions. So you can't put a regular expression into the left-hand side of any one of these formulas. If you want to use a regular expression, well, then you're kind of stuck with case when. But they're both good options for dealing with these kinds of data issues. Fourth dashing issue, the duo. So 2 functions now for working with strings. Buffy on the left, Willow on the right. Supposing our data looks like this, a vector of strings. And you want to take that vector of strings and collapse it down to a single string. This is something that we end up doing quite frequently. We do a lot of automated reporting, and very often we have a string of values that we want to concatenate together, insert into a sentence in a template, and then use it for a report. So how would you go about concatenating these? Well, obviously, paste from base R. I could see Julia sitting in the front here grimacing. Clearly, she's done this before and wondered, what the hell, right? You paste that vector, and it just doesn't do what you expect it to do. Why? Well, because paste has got to paste stuff where you specify each individual string as a separate argument, and then it'll very happily stick them together for you. But don't pass it a vector. You can use the collapse argument. So if you use the collapse argument, you can then specify just exactly what it is that you want to use to stick those individual strings together. And you could choose a space, or if these are going to go into a sentence, you've probably got to use a comma space. You may be disturbed by the fact that there's no and between those last 2 elements. That would trouble me as well, right? I don't want to produce a document that's just got a whole series of things separated by commas. We'll get back to that issue in just a moment. We've got our hero, string flatten. This does the job straight out of the box, right? Takes our vector of strings, smashes them all together. Just one problem. It smashes them all together with nothing in between. So they're now completely adjacent to each other. This is definitely not what I would want. We can use the collapse option, right? Comma space, and this will do precisely what I want. And as it happens, our sidekick function, string flatten comma, does this out of the box as well with no requirement of additional arguments. It also enables us to deal with that niggling issue that I mentioned before. It has a last argument. And this then enables me to say, well, connect everything together with comma space, but between the last two elements in the vector, insert comma and, right? Oxford comma right there. Our fifth dashing duo. Sheldon, the hero, representing safely, and Amy, the sidekick, representing insistently. One might argue that, in fact, Amy is the hero here. Now, I mentioned before that I really like Python. One of the things I like most about Python is the flexibility that you have in handling errors and exceptions. Not so much in R. I always get a bit frustrated with try and try-catch. Let's have a couple of functions to work with here. So firstly, I've got a function called Sheldon is hero. It produces a text message and then generates an error saying Sheldon is not the hero. I have a second function, Amy is hero, which returns true. Now, if you're working interactively with R on the console, then having an error generated like that is absolutely fine. But if this is happening inside a script, well, it's going to break your script, and you're going to have to fix it. Right? So this is not ideal. What you really want to do is somehow deal with that error in your code without stopping anything. So you can use try to do this. Right? You wrap the function call in try, and the result can be assigned to a variable. That variable either ends up with a legitimate result if there's no error, or an error object, which you then have to deal with in your code. The safely function, our hero, allows us to wrap a function. Now, in Python, this would be called a decorator. In the Tidyverse, an adverb, I guess, enhances a verb. We get back another function. So Sheldon is hero safely, and that will return a result, which is now a list with two elements, result and error. And you can see in this case, result is empty, and error is full. So this is nice and easy to pick up in code, and furthermore, it doesn't stop your code. With Amy, there's no error, so we see that the result, true, is populated, and the error is empty. If you want something simpler, well, then there's possibly. And here you can specify an otherwise argument. So what to do if there's an error. And this really is my preferred approach. Doesn't give you the flexibility of Python, but it means that you get back just a single thing to deal with. So in this case, my wrapped function returns false for Sheldon is hero. What happens if you want to iterate in the case of failure? Well, this is where the sidekick enters. Insistently, this allows you to take whatever function is that could potentially fail and set up some infrastructure to run that function multiple times. Do this via the insistently function or wrapper, and you can specify just exactly how many times and how frequently to run that function. So here, we've got exponential backoff set up so the delays get progressively longer between each of those. When we run that, we see that it runs the function 4 times and that the delay gets progressively longer if you look carefully at the timestamps. Ultimately, though, you end up with an error. So here we have a very nice example of our hero working with the sidekick. So we can take all of that and wrap it up in possibly. So we now have 4 iterations and finally a value that is not an error. Oh, and finally, conclusive evidence that Sheldon's not the hero. Okay, in reality, I think that all of these functions are heroes in their own right. And if you aren't using them at present, you should, because they will make your work with R easier and more fun. And I think that's what it's all about. Finally, a quick plug for a package that we're working on internally at Fathom Data. If you send emails from R, then check out Emaili. It's Tidyverse compliant. It has its own share of heroes and sidekicks, also no villains. And I'd like to thank my colleague, Bianca Peterson, for her help in putting this presentation together.